So related to the hierarchical clustering and the previous question from the student, sometimes you want to decide how many groups you want to do, and that's called a partition cluster. For example, I want to describe my gene behavior into 6 different groups. I say this group of genes keep on going up, that group of genes up and down, and another group, just keep going down or something. You want to decide how many groups you do, and you partition all of your genes into disjoint groups. And so remember, a hierarchical clustering, basically, eventually, all of the genes will belong to one huge cluster, which includes all the genes. Whereas partition cluster, if a gene belongs to one cluster, it would not belong to another. And the very simple way to get to this disjoint group is, you can imagine if you have a hierarchical clustering already, you have to choose, I want to have 3 groups or 5 groups or 10 groups. But once you have the tree, you can just decide where you cut this line, and anything below that line is disjoint groups. Right? So for example, if I cut the line very high, I will only have 2 groups, this group and this group. But if I cut a little bit lower, this will divide the samples, or it could be samples or could be genes, into this group. There's a second group, these 2 samples, a third group, and the one sample is one group. But if you cut extremely low on the tree, then every sample or every gene itself can be its own cluster. And so you can choose to just cut at any arbitrary location, so to reach the K that you want. Right? That's one way to get this disjoint partition of groups. Another way to do this is by an algorithm called Kmeans. So we are showing in here, this is the case when you are looking at the genes. I'm only showing you in a 2-dimension way. In reality, there is 20,000 dimensions, right? Let's just look at 2 dimensions. So the x-axis is the expression of this gene in sample 2, and the y-axis is expression of this gene in sample 1, and we are trying to cluster genes based on the distance between the 2 samples. You can imagine in reality, we might have a lot more samples, and also it's too many genes. But let's just look at this in a 2-dimensional way. Initially, by eye, you might think that there are 3, but for algorithm, maybe initially it doesn't know. So it just randomly pick 3 locations as the center. So these are the green, red, and brown color. And you just pretend this is the center of the cluster. So by the way, if you do Kmeans cluster, you have to choose a K. Let's in this case say K equals 3. And you randomly pick some centers, and based on that center, you calculate the distance of every gene to every center, and then assign that gene to the closest center. So for example, these 2 genes, these 2 genes are close to the brown, so they're being assigned to the brown color. These 2 genes, look kind of, if you calculate the distance of this gene to the brown, the red, and the green, it's only slightly closer to the brown. And so, okay, fine, we'll just assign it to the brown group. And these 3 genes are distance-wise closest to the red, you assign them to the red. And based on that assignment, you calculate their average together, and to create the new center for that cluster, okay? And so you can see these 4 samples, these 4 genes are really far apart, but whatever, we'll just, for now, calculate their average, which is around here. And with these 3 genes, their average is kind of, they are pretty close to each other. And this green one, you can see the cluster center is not so great, but don't worry, let's just calculate their average in here. And the next round, we will use the new cluster center to reassign the center, to reassign the dots. For example, for this gene, we're gonna calculate its distance to the red center and the brown center. And you will see that it will be assigned next time to the red because it's closer to that red center. And this, maybe this green sample, initially it belongs to the green, but if you now calculate its distance to this brown center versus the green center, you will believe that it belongs to the brown group. Right? So by the next time you calculate their average, oh, that's pretty good, right? They really go with their group. And when does this stop is all the groups are assigned, you run it again, they don't change their grouping anymore, then you converge, okay? And sometimes there are some genes, supposedly it's in here, right in between the brown and the red. And so depending on how you change, it might change a little bit to here, next time it's assigned to there, but if overall this cluster has been pretty stable, you can converge and stop the iterations. So you can see here, this is actually a iterative process. You pick the K, and every time you randomly assign some cluster center and reassign the points to the cluster center, and then reestablish the cluster center and repeat until you converge. So question is, if you pick the cluster center first, in this case, we start somewhere, some random thing, would we always converge to the same thing at the end? Would you always converge to the same thing at the end? Actually, you will. The randomness comes from starting at a different starting point. But once you pick the starting point, it's a very deterministic way. Everything finds its closest point, and then they form the new cluster and then continue. It's a deterministic process. So you might want to restart a number of times just to make sure that you converge on the right thing. But if you start at the same place, you will always end in the same place. Question? I was going to say, but isn't it possible based on where your initial assignment is that some clusters are empty? Yes, if that cluster is empty, yeah, occasionally that would happen. You start with 7, at the end you have only 6 left, right? Yeah, it could happen. So then how would you say it's always but that is because you started at that point already. So once you pick the starting point, there's only one way it will converge. If you will only avoid that situation if you start in different ways. Okay. Is there another question there? So basically you're saying starting at different points can result in different outcomes, but the same input basically. Yeah, okay. Right. If you start at the same place, you will always end in the same place. But if you start at a different place, you will end in different ways, okay? So Kmeans clustering is actually a deterministic method. Once your initial clustering center is set, you will converge in the same way. Occasionally, you can be tracked in some local optimum problem. And so you could actually try to run different things. So for example, how do you pick the initial cluster centers? One way is you run your hierarchical clustering. By the way, is hierarchical clustering deterministic? Yes, it is. And no matter how many times you start, it's going to be the same thing, right? Because you always just calculate based on pairwise distance calculation. So you can say start from a hierarchical clustering and say your K is 5, then I just draw the line cut at 5 and use those as your starting point. Or you can just randomly start many times with initial clusters, and at the end, look at how things converge and then evaluate whether that cluster result is good. How do we evaluate whether the cluster result is good? You evaluate your between cluster distance and within cluster distance. You want the between cluster to be as different as possible, but within cluster as similar as possible. We'll show you some measurements to do this analysis. Unfortunately, this approach may not be very tolerant to outliers or noise. For example, you might see this case. There is one sample. I mean, these ones, you know, that they have a pretty good this is okay. The green cluster is okay. The red cluster is here, but then there's this one guy which is really off. It's quite far, but you know, it's still assigned in here. And so sometimes the cluster center is assigned by averaging all the samples in this cluster, but this center is not representative of your of the average behavior of the cluster. Is because you have an outlier of this. And so sometimes you can also try this partition around moduloid, which is you pick one real data point. But by the way, there could be even crazy cases where the center is like here. It's not in the center at all when this is quite far away, right? And so in order to deal with that, you can pick one real data point that is closest to all of your other points instead of using the average of all the sample or all the dots here to calculate that center cluster, which can give you a little bit more robust result in the presence of some outliers. So in this case, for example, yeah, I think the one without the black circle is the moduloid, which is kind of closest. You always pick the one that's closest to everybody else. That's a real point to make sure that you don't pick a cluster center that's actually quite far away from most of the things. Questions? Yes.
So what do you mean I pick one point that is closest?
So instead of averaging all the points to calculate the center, you pick a real point, because sometimes you might pick an average, but this average is because of one outlier, the average is actually further away from most of the points. And so this partition around moduloid is every time the center of the cluster is always a real data point. You use that, which the sample that's closest to everybody else as your real cluster center. And then you can still reiterate this process. Okay. So at least you pick a real point rather than an average, which is not representative of your cluster. Another question?
For the Kmeans, you have to define how many clusters you want.
Yes.
So you have this, what if it's like you make extra clusters